Welcome to Advanced Group Theory. Today, we are going to explore two of the most powerful and fundamental tools for breaking down complex mathematical groups, centralizers and normalizers. Whether you are studying abstract algebra, quantum physics, or molecular chemistry, understanding how elements interact is crucial. By the end of this lesson, you will understand exactly how to find them and why they matter. To begin our journey into group theory, imagine a large, bustling party representing our mathematical group. Inside, there is a VIP guest. Most people change their behavior depending on who they talk to, which is like elements not commuting. But there is a special circle of friends who interact with the VIP completely naturally. The order of who speaks first does not matter. In group theory, this special circle is called the centralizer. It is the collection of all elements that commute perfectly with our chosen target. Now that we understand the intuitive idea of this special circle of friends, let us define it mathematically. The centralizer of a set A inside a group G is written as Cg of A. It collects every test element G from the entire group that commutes with every single element A in our target set. The equation G times A equals A times G is the mathematical way of saying the order of operations does not change the outcome. If you increase the size of the target set A, it becomes much harder for an element to commute with everything inside it, so the centralizer typically shrinks in size. This commuting property leads us to another way to write the exact same definition, using a powerful concept called conjugation. If we take our previous equation and multiply both sides on the right by the inverse of G, we get G times A times G inverse equals A. This tells us that conjugating the element A by G leaves it completely unchanged. Conceptually, this means the centralizer consists of all elements that do not alter the target when applied from both sides. If the target element changes even slightly during this process, the test element is rejected from the centralizer. Before we move on to abstract proofs, let us see this with a concrete geometric example. We are given the dihedral group D4, which represents all the symmetries of a square, including 4 rotations and 4 reflections. We are asked to find the centralizer of a specific target element, a rotation of the square by 90 degrees clockwise. To solve this, we must test every single symmetry in the group to see which ones commute perfectly with a 90-degree rotation. Let us test the elements to see why some work and some fail. We know from basic geometry that any rotation commutes with another rotation. For instance, a 180-degree rotation added to a 90-degree rotation gives 270 degrees, regardless of which one you perform first. However, reflections do not commute with rotations. Pushing a rotation past a reflection changes its direction, so the order of operations completely changes the final physical position of the square. Because reflections fail the commuting test and change the outcome, they are excluded from our special circle. We conclude that the centralizer consists exactly of the 4 rotations. Physically, this final answer means that only rotational symmetries preserve the exact sequence of operations when combined with a 90-degree turn. If you want to maintain perfect symmetry without altering the outcome of the rotation, you must stay strictly within the rotational elements of the group. This completes our search. Now that we have successfully found a centralizer in a real group, we must prove a fundamental theorem. The centralizer is not just a random collection of elements, but a valid subgroup itself. This chunk of the proof is setting out to establish the first part of the two-step subgroup test. We assume 2 elements, x and y, are already in the centralizer, meaning they commute with A. We want to see what happens when we multiply their product, x times y, by a target element E. By the associative property of groups, we can shift the parentheses to group y and A together. This sets up a crucial substitution step. Continuing our derivation, because y is in the centralizer, We know it commutes with A. Therefore, we can safely replace y times A with A times y inside the parentheses. Then we shift the parentheses again. Since x is also in the centralizer, it commutes with A as well, allowing us to swap them. Finally, we regroup to show that the combined element x times y has completely swapped places with A. The intuition here is that if two elements preserve the target individually, their combination does too. A similar logic proves the inverse is also in the centralizer, giving us our final result. It is always a valid subgroup. So we have proven that the centralizer is a strict subgroup. This brings us to a slightly looser, more relaxed club called the normalizer. Imagine a football team manager who swaps the striker to midfield and the midfielder to defense. The individual players have changed places, but the team as a whole remains exactly the same. The normalizer does exactly this. It shuffles individual pieces inside a set, but preserves the entire boundary of the set. Let us define this looser club mathematically. The normalizer of a set A is written as ng of A. It contains all elements G such that conjugating the entire set A by G returns the exact same set A. Unlike the centralizer, which forces every single element to stay exactly the same, the normalizer only requires that the elements land somewhere inside the original borders. If the set A grows larger, the normalizer has more room to shuffle elements around. Because the centralizer requires strict point-wise fixing, every element in the centralizer automatically qualifies for the normalizer. Let us see how this set-wise fixing works in practice with a new problem. We are asked to find the normalizer of a subgroup H in the symmetric group S3, which consists of all possible permutations of 3 items. Our target subset H contains the identity and the permutation that swaps items 1 and 2. We will test a specific element, the swap of 1 and 3, to see if conjugating our set by it leaves the set unchanged. This approach will reveal if the element belongs to the normalizer. Continuing our calculation, we know conjugating the identity element always gives the identity. So the real test is conjugating the swap of 1 and 2. We multiply the 3 permutations together from right to left. Starting from the right, 1 goes to 3, the middle leaves 3 alone, and the left sends 3 to 1. Tracking all the numbers carefully through each permutation, we find that the final result of this conjugation is the permutation that swaps 2 and 3. We must now compare this to our original set. Because our conjugation resulted in the swap of 2 and 3, the new set we created is not our original set H. The element escaped the boundaries of H. Therefore, our test element failed the condition and does not belong to the normalizer. If we test all elements, we find that only the identity and the swap of 1 and 2 keep the set intact, meaning the normalizer is just H itself. This diagram perfectly illustrates the difference we just calculated. On the left, the centralizer performs point-wise fixing. Notice how every single point inside set A maps directly back to itself. On the right, the normalizer performs set-wise fixing. The points inside set A are permuted and shuffled around, mapping to different points, but the outer boundary of set A remains completely invariant. The set as a whole is trapped. To summarize, both concepts measure how elements interact with a subset. The centralizer is strict, requiring perfect point-wise commuting. The normalizer is more forgiving, allowing internal shuffling as long as the set boundaries are preserved. These are the primary tools for breaking down massive groups into understandable pieces, essential for physics, chemistry, and advanced theorems. You now have the fundamental keys to unlocking advanced group theory.